I'm going to do a couple examples right now looking at the instantaneous center of zero velocity. These are examples just to sort of highlight the different approaches that are available to you with some personal bias given at the same time. I will also mention that I will try and incorporate some of the results from SMath Desktop, which is a piece of software I'd recommended earlier, and include that as a separate file within the video folder. I think Instantaneous Center is a great idea, and there are certain types of problems that work really well with it. And so, for example, you have, say, a rod that is connected here, A and B, and you have a velocity VA, VB. This is a good problem because then the instantaneous center is obvious and you can click and do it right off pretty much right away. However, it's more difficult with some of the problems that I'm going to do, and I'm going to show you two ways. I'm going to do it first of all as I promised, which is an instantaneous center, and secondly as a vector solution. These are problems that, as much as possible, and certainly with all the videos, I do encourage you to try them on your own and just recognize that these are complex geometries. I don't actually recommend in either of these approaches or either of these problems that you actually use the approach I use with instantaneous centers. I strongly recommend the vector approach. We'll start with something not quite as complex as the one that'll follow, but it's still a bit complex. You have a link AB over here, and it's rotating at omega AB of 4 rads per second. And you're asked to find the velocity of the collar C, right over here, and the angular velocity of the link CB, which is right here, at the instant shown. Link CB is horizontal at that instant. And this is really one of the traditional types of tricks we use in an exam because it stops some of the questions you might eventually have. So if I define an XY system, motion is sort of limited in the X direction. So you're given omega AB, which is 4 rads per second. The length of AB, or A right here, is 500 millimeters. B is given as 350 millimeters. And you have theta of 60 degrees and phi of 45 degrees. Now, what you do with all of these problems is the same thing, which is you break it up into parts. So if I look at the link CB, the slider is constrained to move along that green bar, and that green bar is at 45 degrees. And B is constrained here with this motion. So I know what the motion looks like, and I can make a simplified drawing of it. And VB is omega AB CA. Omega BC is velocity of B divided by C, and I can do velocity of C is omega BC D. Okay, so it becomes a little bit complex, but okay. And I can calculate all of these terms when I define my instantaneous center. Super, this is great. It looks not too complex, but drawing these perpendiculars is more challenging than you might expect. And doing it for this one is something that I would not have done normally. If I try it, what I would do is something along the lines of this, which is, well, I would say, first of all, D over sine of little d is included angle, B over sine of B, and C over sine C. And I could calculate each of those terms by saying, well, D is really theta, B, little b over here, is 90 plus phi minus theta, and C is sine of 90 minus theta. This is not a satisfying way to do it, and I don't really like it a lot. And I can calculate all the terms, I calculate all the expressions, and this is how I end up with these final results over here. So I probably should not have given you the answers at the beginning, but that's what happened. On the other hand, I can do an alternate form, and this is not going to look easier because it's going to take more steps, but it is actually, for me personally, I find it's a much better approach to understand the problem. I know that velocity of B is 2 meters per second. That kind of, I'm going to get that from 4 meters, 4 rads per second, and half a meter moment arm from A to B. So I can write that as a vector, and that's in the I, J, and K directions of 0 rads per second, 0 rads per second I and J, and 4K rads per second. Distance for RAB, again, is going to be I, J, and K, but it's A sine theta I, A cos theta J, 0 meters K. And RAB is, of course, this distance A. I know the direction, and I can quickly solve that. And if I do the magnitudes, and I do calculate the magnitudes in this particular case, I end up with 2 meters per second. That's just the magnitude. But I also know right away that I have a minus rad 3 and a positive 1 meter per second. So that kind of makes sense because from an I and J perspective, and this is why it's important to draw these problems out, the X has to stay in the correct direction, Y stays in the correct direction. This is why I obsessively try and draw the axis so that when I look at the problem, I always know what I'm getting in terms of results. To solve for the terms on B, I could say, well, velocity of C is equal to velocity of B plus velocity of C relative to B. And of course, in terms of components, I could say velocity of C in the X direction is equal to velocity of B in the X direction, plus velocity of C relative to B in the X direction, relative and corresponding terms for Y. Velocity C in the Y direction, velocity B in the Y direction, plus velocity C with respect to B in the Y direction. Of course, the notation sort of means that this term will cancel out, and I'll get that velocity C that I want. Anyway, yeah. Velocity of C with respect to B in the X direction is going to be the distance RC with respect to B in the Y direction, which is equal to 0, because C and B are both at the same height. And so they have 0 distance. So I know right away by inspection, this problem will get rid of that term. Velocity C in the X direction is now going to be velocity C cos theta, and I'll end up with velocity C, which is equal to minus 2.45 magnitude meters per second. Right. Velocity C in the X direction is equal to velocity B in the X, which is velocity C cos phi, and velocity C equals V B X over cos phi. I'm just writing that extra step. I can substitute in terms. I've got phi here. I've got RBCX. I've got omega BC, which I don't know. And I have velocity B in the Y direction. Well, I have all of the terms there that I need. I also have velocity of C. So I have check, 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 check. And I end up with this term right here. So I have omega BC of 7.81 rads per second. That worked out really well. It's kind of nice. And it kind of makes sense in terms of the final velocity. Now, I also can calculate out the terms, and velocity of C should go in this direction. Now, that's kind of an intuitive result, but I'd kind of expect to get, minus VCY and a minus VCX according to the notation I've used. Both ways are valid. Get the same result. Everything is the same. However, again, this is a personal bias, and you may be really good at geometry, and you may find this overly a bit too much work. But I do find that there's much more risk of error when it comes to using the instantaneous centers. The vector approach requires you to draw the solutions, and when you do this, you see the possible errors more easily. As a first step, you solve for the terms. You solve for the radial directions. You solve for everything right away. Now, I should also mention, I did this problem with SMath Desktop, and the reason I'm using SMath Desktop for this is because it's free, and it gives you all of the capabilities immediately. So I can include matrices, I can do integrations and things like that I can't do in MathCAD Prime, which I like a little bit better in terms of its input methods, but free is free. If I didn't do it, by the way, please remind me. Now let's try a really complex problem. This is a problem that you can solve a whole bunch of different ways, but here is something where I have velocity of A given to you. The mechanism consists of a driving position A over here, 3 members, and a riveter which is attached to the slider block D, which is now constrained to move up or down. Determine the velocity D at the instant shown when the piston at A is traveling at velocity of A. So you're given RAC, which is 300 millimeters, RBC, which is 200 millimeters, and RCD, which is 150 millimeters. You're given this is equal to 300 or 30 meters per second. And I should give you all the angles. Theta 1, theta 2, theta 3, theta 4. So theta 1 is right here, which is 30 degrees. Theta 2, which is 45 degrees. Theta 4, theta 3, and theta 4. Theta 3 is 60 degrees. Theta 4 is 45 degrees. Again, these are typical lecture problems. Will use these 3 angles in most cases. And I may do a couple of problems, and I do a couple of problems where I go a little bit off because I have a little bit more time in these videos. So I've given all the angles and all the distances. And the other thing is that I kind of know where the directions are. So as I expect that velocity, or I know velocity of A is going up and to the left, I expect that the length BC is going to be rotating in the counterclockwise direction, and I expect that the velocity of D is going to be moving downwards. That's intuition, and in this particular motion, it's complex-ish. It's actually quite complex, but it's kind of useful to try it out and think about this. I can do this as an instantaneous center, and if I do that, I'd say, well, first of all, the length CD and the length AC. When I do all the calculations, I can calculate instantaneous of centers of IC and CD, and I can calculate all of these terms, and clearly what I'm going to try and do is use the law of sines. And I can calculate theta 4, which is given. I get delta, which is theta 3 minus theta 4. I get epsilon, which is 180 minus theta 4 minus delta. And I get alpha, which is theta 3 minus theta 2. Gamma, which is 180 minus alpha minus beta. And beta, which is 90 minus theta 2 plus theta 1. This comes from the geometry. You can do it yourself. And again, if you can go back and look at the terms and calculate how to do these expressions. So I end up with this, and I get all the terms, and I get the velocity at point D at the very end. And what I'm going to do is say, well, here's the link from the instantaneous centers. From that, I can calculate omega AC, I can calculate omega C, I can calculate velocity of D, and I end up with 10.6 meters per second. Okay. Again, I don't like this approach. It's not difficult in the sense that once you are familiar with the geometry, it works very well. But at this stage, it's often easier to start with these problems from a different approach. What we can do is velocity A and velocity C. Now, bear with me because in this particular problem, to make this work, I'm not going to write out everything. So again, the SMath desktop has all the calculations and all the terms, and I've also put some of the values here if you do want to try this on your own. Now, we're given A in the slot, there you go, and I can say, well, first of all, it's at 45 degrees, so you get 21 and 21, negative 21, because it's moving to the left in the I direction and upwards in the J direction. Velocity of A is equal to velocity of C plus velocity of A with respect to C, or velocity of C is equal to omega VC cross RVC, velocity AC, omega AC, RAC. I can then transfer that same velocity, which I've just calculated or been given. This is a given value, and put it onto the other term. So if I do that, velocity of C is equal to minus 25.1 rads per second, or 25.1 plus 14.5 I and J respectively, meters per second. And omega AC and omega BC can be calculated directly from there. Now, if omega AC is calculated, it's 25.88 rads per second, and you have to recognize that what I'm doing here is saying that this B is here, and this is acting at a normal. So if you do that, you have velocity of D, which is velocity of C plus velocity of D with respect to C. Velocity of D is going to be in the minus y direction. And you can see that red arrow pointing in that direction. Velocity of D with respect to C is going to be omega CD crossed with RDC. And I end up with the same value of minus 10.6 meters per second. I have gone through a very, very high level approach in terms or discussion on that particular problem. However, again, the problem is available offline, and I put more details in terms of the notes. The vector approach, again, as far as I'm concerned, is really much, much better. The solution is amazing. I mean, you get a lot of information from just following a careful step-by-step approach. Again, I apologize, I didn't go through all the steps. It's a lot. However, what you do get out of it is quick and relatively straightforward. The instantaneous center approach works, but really it's so much work. The geometry has to be carefully defined, and an error in terms of the calculations. And I find I make a lot of errors when I'm doing things like calculating these alpha, betas, and gammas that I defined here. The last problem takes a lot of time, and I do kind of encourage you, if you have the time, to try it on your own. There is enough in the presentation to give you that. So the SMath desktop solution will also be available for this particular problem. It's in the same file. And one of the things that I tried to do was give you some of this information here, because you wouldn't necessarily know how fast omega AB and AC and BC are. Again, thank you very much, and stay away from instantaneous centers if you